So, hello everyone. So, in the last session, we have solved few problems related to the type 1, type 2 systems related to the positional velocity and acceleration error coefficients. So, we are going to continue with two more important problems. So, this is the third problem, that is for a unity feedback system, the open loop transfer function is given as g of s is equal to 10 into s plus 2 divided by s square into s plus 1. Since they have mentioned it as unity feedback system, so we have only considered the g of s since h of s is equal to 1. So here we need to find the values of kp, kv and ka, and also we need to find the steady state error when the input r of s is given as 3 by s minus 2 by s square plus 1 by 3s cube. Okay, so this problem is similar to the problem which was solved at the last session, the last problem. Here there is a slight change in the transfer function as well as the input. So in the last time they have given the input in case of time domain. Here they have given in case of s domain. Okay, this is again also the combination of step, ramp and parabola, all three of them. Though there are few slight changes, but the problem remains the same. So now let's solve it quickly. Okay, first write the transfer function, open loop transfer function, that is g of s into h of s is equal to 10 into s plus 2 divided by s square into s plus 1. Okay, so we need to arrange it in the general form. Okay, that is taking this 2 outside, that is it would be 10 to the 20 into 1 by 1 plus s by 2, right, divided by s square, and taking this 1 outside, so it remains s square only, 1 plus s. Okay, so this is the way the general form the transfer function is written. Okay, so now one by one let's find all the values of kp, kv and ka. So first thing, kp, the formula is limit s tending to 0 g of s into h of s. Okay, so kp is equal to limit s tending to 0 20 into 1 plus s by 2 divided by s square into 1 plus s. So kp is equal to, apply the limit, so 20 into 1 plus 0 by 2 is 0 divided by s square, so 0 into 1 plus 0, so our final value we are getting it as 20 divided by 0 is again anything number divided by 0 is infinity, so kp is equal to infinity. So quickly let's find kv. The formula for kv is limit s tending to 0 s into g of s into h of s. So kv is equal to limit s tending to 0 20s into 1 plus s by 2 divided by s square into 1 plus s. So 1 s would be getting cancelled. So kv is equal to limit s tending to 0 20 into 1 plus s by 2 divided by s into 1 plus s. So kv is equal to, apply the limits, 20 into 1 plus 0 by 2 is 0 and 0 into 1 plus 0. So again we are getting 20 by 0, that is again infinity. Okay, so similarly find the value of ka, limit s tending to 0 s square into g of s into h of s. So ka is equal to limit s tending to 0 20 s square 1 plus s by 2 divided by s square into 1 plus s. So s square gets cancelled. So ka is equal to, directly apply the limits. So okay, let's write that step. 20 into 1 plus s by 2 divided by 1 plus s. So ka is equal to 20 into 1 plus 0 by 2 is 0 divided by 1 plus 0, that is equal to 20 by 1. So our final value of ka, we are getting it as 20. So these are the values of kp, kv and ka respectively. Okay, so now let's find the second case, that is steady state error when the input provided is r of s is equal to 3 by s minus 2 by s square plus 1 by 3s cube. Okay, so again in this case we can see that this is the combination of step, ramp and parabola, but here in this case it's in the s domain. So in s domain, step signal is represented as a by s, ramp signal is represented as a by s square, and parabolic signal is represented as a by s cube. So similarly here For step signal, the value of A is equal to, in place of A what we have here, 3, so A is equal to 3. For amp signal, in place of A what we are having, -2. So in place of a parabolic signal, the value of A is equal to 1 by 3s cube, so 1 by 3. Okay, so these are the values of the amplitudes. Okay, so now one by one we need to be finding the steady state errors for all the signals. For step signal, ESS1 is equal to A divided by 1 plus Kp. A is 3 divided by 1 plus infinity, so it is equal to 3 by infinity, it is equal to 0. Okay, similarly for ramp, ESS2 is equal to A divided by Kb, that is -2 divided by infinity, that is again 0. Kb is infinity, right? For parabola, ESS3 is equal to A divided by Ka. Okay, that is 1 by 3 divided by 20, right? So that is 1 by 60. So these are the values of ESS 1, 2 and 3. So after the addition of these three total, ESS is equal to 0 plus 0 plus 1 by 60. So our total steady state error, we are getting it as 1 by 60. Okay, so yeah, this is the solution for this. Nothing much changed, but only in this problem the change here is, in place of time domain they have represented it in the Laplace domain or the frequency H domain. Okay, so this was the problem. So please try to solve this very simple problem. So hello everyone, so welcome to this session. So in this session we are going to see with the analysis of the first order control system. Okay, in the module 3, that is time response specification. Okay, so now these are the some of the few sub derivations which are very important ones, that is analysis of first order system, second order system and their unit step responses. Okay, so there are many derivations from now, so we need to be concentrating very well. And also in the last session we have discussed about PI/PD controllers, right, and also PID controllers and one program related to that. Those are also very important, multiple times repeated. Okay, so let's get to this concept now, analysis of first order control system. Okay, so that is consider first order, consider a typical circuit here, network. So if the system is excited by a unit step, okay, so we can say that unit step, that is Vi of t is equal to 1 when t is greater than or equal to 0, and for unit step it is 0 when t is less than 0. And also if we take this Laplace domain, what you would be getting, Vi of s is equal to 1 by s. Okay, since for unit step response it is 1 by s. So again redraw the circuit when we consider it from time domain to s domain or Laplace domain or frequency domain. The value of R would be remaining as it is. The capacitance would be replaced by 1 by Cs. Okay, and when if there is an inductance term, it would be replaced by Ls. Okay, you might be knowing it, we have discussed this in the first module also. So Vi of s, V out of s. So again try to write the equation, that is Vi of s is equal to R into I of s plus 1 by Cs into I of s. So V out of s also is equal to 1 by Cs into I of s. Okay, so that's why the relationship between the output and input, that is the transfer function V out by Vi is equal to, substitute the value, that is 1 by Cs into I of s divided by R plus 1 by Cs into I of s. So we can cancel this I of s and I of s term. Okay, we would be remaining it with the term 1 by Cs divided by R plus 1 by Cs. So in the denominator term, take the LCM and solve it, that is 1 by Cs divided by RCS plus 1 divided by Cs. So here Cs would again get cancelled. So our relationship between output and input, that is the transfer function V out by Vi, we are getting it as 1 divided by 1 plus RCS. Okay, since we know that T is equal to RC, okay, in the time domain function the R and C components are getting added up, so that's why T is equal to RC. So we can say that 1 divided by 1 plus RC is replaced by T, so 1 divided by 1 plus TS. that is equal to V out by Vi. So finally the transfer function which is obtained for first order is V naught of S divided by V I of S is equal to 1 divided by 1 plus Ts. So in this way we need to be analyzing the first order control system here. Okay, this is just for your reference, this is not so important. Okay, so the next derivation is very important, that is for the unit step response of the first order control system. Okay, so now what is this unit step response? So now that is we need to be considering again put the Vi of S, that is the input source, that is equal to 1 by S. Also V out of S is equal to 1 divided by S into 1 plus RCS. Okay, so here in this case we need to be taking the partial fraction here. Okay, that is a dash divided by S plus B dash divided by 1 plus RCS. Okay, partial fraction method. Then 1 by S into 1 plus RCS. So cross multiply and take the LCM, that is A dash into 1 plus RCS. This is a basic max, you might be knowing it. Cross multiplication, that is A dash into 1 plus RCS plus B dash into S divided by S into 1 plus RCS, so that we can cancel these two terms out. So we are left with A dash into 1 plus RCS plus B dash into S is equal to 1. Okay, so multiply this A dash to both the terms, that is A dash plus A dash RCS plus B dash S is equal to 1. So A dash plus S is common here, so take S outside, so that is S into A dash RC plus B dash is equal to 1. So now here in case of S we can see that, consider the powers of S, that is 1 can be also written as 1 into S to the power 0 plus 0 into S, right? 0 into S is 0 and 1 into S to the power 0, so we can see that the value of A dash is equal to 1. Okay, since the power of S to the power 0 is 1, so the value of A dash is equal to 1, and also A dash into S into A dash RC plus B dash, that is A dash RC plus B dash is equal to 0. Okay, that is RC plus B dash is equal to 0. So why this A dash RC plus B dash is equal to 0? Because we have S into A dash RC plus B dash, right? We are considering the coefficients of S to the power 0 here. Okay, so that's why this is the coefficient of S to the power 1, so that's why this whole term would be equal to 0. So if we equate this whole term to 0, what we would be getting? RC plus B dash equal to 0 if we take this A dash to other side. So that's why we are, since the value of A dash here we got it as 1, so that's why RC plus B dash is equal to 0 and B dash is equal to minus RC. Okay, so in this way we are getting the values of A dash and B dash. So now substitute that values of A dash and B dash again in this equation, that is V out of S is equal to 1 by S. So the value of A dash is 1, so 1 by S minus plus B dash, so value of B dash is minus RC, so minus RC divided by 1 plus RCS. So 1 by S is equal to, so now divide both numerator and denominator by RC, that is RC by RC divided by, so this we are doing this because we need to be taking the inverse Laplace transform. In order to bring it to that form we are taking it, so that's why RC by RC divided by 1 plus SRC divided by RC. Okay, so that is V out of S is equal to 1 by S minus RC by RC is equal to 1. Okay, so that is, then we can take S common here, S plus 1 by RC, that would be getting it as RCS plus 1 divided by RC, so that's why S plus 1 by RC. Okay, so that's why that is 1 divided by S plus 1 by RC. Since this is of the form 1 divided by S plus A, okay, we can take its inverse Laplace transform in a very easy manner, so that's why. So now take replace this S domain by T domain, that is by taking the inverse Laplace transform. So this would be V out of T is equal to the inverse Laplace transform of 1 by S is equal to 1, so minus 1 divided by S plus A. Okay, that is equal to e to the power minus AT. Okay, but in place of A we are having the value of 1 by RC, so e to the power minus T by RC. So this is the value of V out of T. So whenever RC is increased, so whenever the value of RC is getting greater and greater, so if it reaches to one stage it would be reaching to infinity, so that's why the answer would be, we are getting it as e to the power minus T by RC. Whenever the value of RC is getting greater and greater, the value of this term would be equal to 0, so it would be diminished. So the final value of V out of t, whenever the value of RC is increased, we would be getting it as V out of t is equal to 1. That is the unit step response. Okay. So in this way, the analyzation of unit step response is very, very important. So please go through this derivation once again. This is very, very important one. So this is one simple program here. You can see here of PI and PD controllers. Okay. So here, let's see here in this program first, right? They aim to analyze and implement the PI and PD controllers using inbuilt MATLAB. Okay, so in this case, we need to be using the software called as MATLAB. Okay, it is available in your Google, or you can download it if you want. MATLAB 2007. All the programs and all we would be doing in that only in order to get this kind of outputs here. Okay, yeah. So here, this is the first program here. You can see this is a simple program. So first take a simple transfer function, okay, which having both numerator and denominator, and write them in form of num is equal to 1 and den is equal to 1, 3, 1, that you might be knowing. That is writing the coefficients and all. Then declare a variable called as g with the opcode of tf, which defines as the transfer function of numerator as well as denominator. It would be giving, if it would be solving this, and it would be giving you an expression. And this h represents the feedback. Okay, that feedback path. Okay, then this is the unity feedback, so that's why it is given as 1. So m is equal to feedback of g comma h, that is these both are the feedback, right? So if we want to convert it into a single block, this command you will be using. Then step of m, then hold on, then kp, ki, kd. I've told you, right? The kp is the proportionality gain, ki is the error constant, and kd is the derivative constant. So we need to be giving different values for this. Okay, if you the program remains the same. If you change the values, these three values, you will be getting desired outputs as different waveforms with the different timelines. That is a peak time, rise time, settling time, and all. Okay, then declare one more variable, capital letter G, then PID, that is proportional plus integral plus derivative controllers PID, then of KP comma KI comma KD, then MC is equal to feedback of G star G comma H, that is multiplication of the transfer function along with the required output of PID controllers. Then we have declared it using the variable MC. It is the controllers. Then step of MC, then we will be getting the desired output for that as well. Then grid on, this is optional. Okay, if you don't provide this, the you can see these grid lines here, right? The horizontal and vertical lines, that won't be occurring. Okay, if you put this a command grid on, these lines should be occurring here, and this is the output generated here. You can see. Okay, so this is the output generated for the. So this is the output generated for the first program which I've told here, where the values of KP, KI, KD are 24, 8, 0. When we set the value of KP as 24, KI as 8, and KD as 0, so this is the response which you are getting here. Okay, you can see the response here. This is the response. Okay, where you can see we are getting two curves here, and this is the peak time. Okay, it's approximately around, we can see the time here. It's approximately around 0.8 seconds. Okay, this is the rise time. Rise time is approximately around zero point 0.3 seconds, and this is the settling time, that is 0.98 seconds. Okay, yeah. So, yeah, so this is 6.98 seconds. Okay, so in this way, we need to be writing a program for PI and PD controllers. Okay, so this question was there in the model question paper, so that's why I've made you see this program. Okay, so that's all for this session. So hope you like this session of PI, PD controllers and all. So please refer these videos and refer whatever I've displayed in the screen, and make a note of it, because the theory questions might be asked in the exams. Okay, so that's why please like, share, subscribe, and refer our playlists. Okay, so that's all. Thank you.